Hello everyone. In this lecture, we are going to see about oscillators in RF transceivers. In oscillator, we are going to see about particularly colpitts oscillator. In RF frequency, that is radio frequency applications, the colpitts oscillator is a popular choice for generating stable and tunable oscillations in the RF frequency range. It is commonly used as a local oscillator in radio receivers and transmitters, and it is also used in various other communication systems. The advantages of using a colpitts oscillator in RF applications, it includes simplicity, low cost, wide frequency tunability, and it can be easily implemented using discrete components and easily integrated into an RF integrated circuit, and it is very compact for monolithic integrated circuit. The figure shows the feedback configuration of colpitts oscillator design. In the feedback circuit of colpitts oscillator consists of two capacitance C1, C2 and one inductance L3. It makes a tank circuit for colpitts oscillator. The figure shows the colpitts oscillator circuit. It consists of two parts. One is amplifier stage and another one is feedback network. This feedback network is called as a tank circuit. It consists of two capacitors C1 and C2 and one inductance L. This amplifier stage is responsible for providing gain or amplification of a signal. The feedback network takes a portion of output signal and feeds it back into input of the amplifier stage. This feedback signal is appropriately phased and amplified by the gain stage before being fed back into the circuit. The feedback network determines the frequency of oscillation and waveform of the output signal. The reactance of capacitance C1, it denotes X1 is equal to 1 divided by omega C1, and the reactance of capacitance C2, it is X2 is equal to 1 divided by omega C2. The reactance of your inductance X3 is equal to omega into L3. Let us see the design steps involved in colpitts oscillator. First, we need to replace the transistor by its H parameter model. In this figure, this dotted box is the H parameter model of transistor. The C1, L3 and C2, it includes the tank circuit of oscillator. In this figure, H11 denotes input impedance, H22 is the output impedance, H12 is the reverse voltage gain, and H21 is the forward current gain. We have three loops in this equivalent model. I1 is the loop current in loop 1, and I2 is the current in loop 2, and I3 is the current in loop 3. Here we are having two voltages V1 and V2. V1 is the input voltage existing between base and emitter terminal. V2 is the output voltage existing between collector and emitter terminal. For this circuit, we are going to apply KVL for all the three loops. So apply KVL for loop 1. So this is loop 1. H11 into I1 minus J XE1 into I1 minus I3, because I1 and I3 are flowing into capacitor C1 in the opposite direction, and is equal to minus H12 into V2. For this equation, we need to find the value of V2. So V2 is the output voltage. It will be existing between C and E, that is collector and emitter terminal. So 1 by H22 into I2 and minus H21 divided by H22 into I1. So we are going to substitute this V2 into this equation. We will be getting this equation. So minus H12 is common for both the two terms. So we are separating these two terms. So we are taking these two terms into this side. Next, we need to arrange this equation according to loop currents. These three terms is having I1 components. So H11 minus J XE1 minus H12 into H21 divided by H22 into I1. For loop current I2, H12 1 divided by H22 into I2, and for I3 plus J XE1 into I3 is equal to 0. So this is the loop equation for first loop. For similar process we have to follow for loop 2 and loop 3. So next we are going to apply KVL for loop 2. So this is loop 2. So 1 divided by H22 into I2 minus JXE2 into I2 plus I1, because I2 and I3 are flows in the same direction. Then plus H21 divided by H22 into I1 is equal to 0. Here also we are going to rearrange the equations according to the loop currents. H21 divided by H22 into I1 plus 1 by H22 minus JXE2 into I2 minus JXE2 into I3 is equal to 0. So this is the loop equation 2. Then we are going to apply that KVL for loop 3. In loop 3 we are having C1, C2 and L3. So for C2 minus JXC2 into I2 plus I3 plus JXL3 into I3 minus JXC1 into I3 minus I1 is equal to 0. We are also separating that equations in terms of loop currents. So we are having 3 loop current equations. So we are going to form matrix for the unknown currents by using 3 loop current equations. So this is the matrix form of unknown currents. In Colpitts oscillators, for finding the loop currents and the value of capacitor and the frequency of oscillation, first we need to find determinant for this matrix. After finding the determinants, the equation contains real and imaginary parts. In that imaginary parts, we are going to set is equal to 0. So then we solve. After solving that imaginary part, we are getting F is equal to 1 divided by 2 pi into 1 divided by square root of C1 into C2 and square root of H22 divided by H11 plus C1 plus C2 divided by L3. This is the frequency oscillations of Colpitts oscillator. Then setting the real part is equal to 0 and assuming H12 is very less than 1, It yields a quadratic equation in terms of this capacitor ratio, that is C1 divided by C2. It is C1 square divided by C2 square into H11 into H22 minus H12 into H21 minus C1 divided by C2 into H21 plus 1 is equal to 0. Under the assumptions that H21 square is greater than 4 into H11 H22 minus H12 into H21, that is 4 times, it will be very higher value. So apply this condition in this equation. After simplification, we will be getting C1 is equal to H21 divided by H11 into H22 minus H12 into H21 into C2. By using these two equations, that is frequency equation and the capacitance equation, we can design Colpitts oscillator for the radio frequency ranges. The preceding treatments deals with the H parameters as real quantities, an assumption that generally may not be applicable. In fact, even for moderately high frequencies, the H parameter attain a significant phase angle. So we are using these two equations. We can design any Colpitts oscillator in the range of radio frequency. Thank you.